right, assalamu alaikum guys. After talking about determinants, probably you tried to do some exercises and you found, well, if your matrix is of large size, then it is annoying to do the computations by hand. Try to imagine you want to use the cofactors and the minors for a 5 by 5 matrix. How much computations do you need to do? And that is easy, but at the same time, it is awkward. It is annoying. Okay, and that always in mathematics, when we have a method that is too long, we try to find an alternative way of doing it. Okay, so today I'm going to talk about another method, which sometimes could be easier, could be shorter, could be more convenient. Okay, if you remember when we talked about elementary row operations, we said you use elementary row operations to transform your matrix into an echelon form. Now, if you remember in the echelon form, it is a triangular matrix, correct? If you are talking about square matrix and you do elementary row operations to get echelon form is a triangular matrix. So we know from our previous lecture that if your matrix is triangular, then the determinant is going to be the product of the elements along the diagonal. Okay? So now the question is, okay, when we moved from the original matrix to an echelon form, we know how to find the determinant of the echelon form that we have. But the question is, as we move along, what happened? Okay? And in that case, we need to see what is the effect of each step we do. In particular, what is the effect of the 3 elementary row operations that we do? Okay? By the way, I'm always talking about row operations, but you can do column operations if you wish, okay? But I like to focus on row operations. Then we can talk about the relationship between the matrix and its transpose, and in that case, it's obvious that it can be done on columns, okay? So the first thing is when we multiply a matrix by a constant, let's say here a non-zero constant. When we multiply a row of a matrix by a non-zero constant, what happens? So we have a matrix, square by square matrix. Here it is. A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. And you multiply any one of the rows by a constant k. Here it is, constant k. Okay, what happens? So you have a matrix A, and here you multiply the ith row by k to get a matrix D. So here is B, everything is the same except the ith row, I, and we multiplied that by k. What is the effect of that? The effect of that, determinant B is going to be k multiplied by determinant of A. Think about it. Why is that? Well, from here, using the formula that we found from the cofactors, you can use this row to write your formula, correct? So here, if you want to verify this, the verification is easy because determinant A here is going to be summation. Do you remember the formula from last time? A, I, J, C, I, J. And here J is from 1 to n. So here I'm using the ith row to write the determinant. Now, if you do it here, this will give you determinant of B equals, well, let's use this row to get the determinant. So that is going to be summation K, A, I, J, C, I, J. And here, J runs from 1 to n. Look here, K shows up in here. It doesn't show up in Cij. Why? Because each time you evaluate Cij, you are going to cover this row. So basically, K will not show up here. So this Cij is the same as Cij here. Okay? And the only difference is K is showing up here. But you know from calculus 2, in the summation, you can take this K out, correct? So if you relate now this with this, the difference between them is this K, correct? So determinant of B is going to be K multiplied by this quantity. And that's exactly what I have here. Determinant of B is K multiplied by determinant of A. So that is a very good fact we got. If you multiply a row of a matrix by constant K, then the determinant of the new matrix is going to be the determinant of the old matrix multiplied by K. Okay? Now, here I must emphasize the following. Doing this is different from multiplying a matrix by K. So here, important remark. If A is an n by n matrix, then determinant Ka, what is determinant Ka? When I write Ka, what does it mean? Does it mean this? No, it means we are multiplying every entry in that matrix by K, which means we are multiplying each row by K. So if you use this fact, it means from each row you are going to get K, and in that case you are going to get K exponent n determinant of A. So please don't mix this with this. Here we are talking about multiplying one row by K. Here we are talking about multiplying the whole matrix by K. Okay? Usually students mix this one with this one. Please don't mix between them. All right, so now we understand the effect of multiplying a row by a number K. When we interchange two rows, what happens? We multiply a row of a matrix by a non-zero constant K. What happens? What happens? So let's go back here and think about you interchange two rows, this here or this here. What happens? So this is your matrix. And instead of multiplying by K here, what you do, you come and, well, let's say here the first row and the second row. So I'm going to change this. And here, interchange two rows. Interchange two rows. So I want to make it easy, just the first two rows. So this is A21, A22, and here A2n, and here A11, A12, A1n. So you can see here what happens. We interchange those two, we get B. What is the relationship between determinant of A and determinant of B? Look here. If you come to write the determinant using the first row, what do you get here? It will be the same as if you here do it using the second row, but that is going to contribute here a negative sign in the cofactors, correct? So doing it using the first row here, or using the second row here, if you do it here using the same row that you interchanged, that is going to contribute a negative sign to determinant of B. Determinant of A. I'm not going to write that, but you can see it right away. So that's going to be -1 determinant of A. And the reason is because we can use that here to get the same thing, but in that case, the difference will be in the cofactors, okay? And that will be a negative sign. So here we get determinant B is -1 determinant of A. So that is the second elementary row operation we can do, and here is the effect on the determinant. What about the last one? The last one, if you multiply a row, when we multiply a row by constant and add it row by constant and add it to another row. What happens? Okay, think about it. So here is a matrix. We are multiplying a row here by constant and adding that to another row. So let's say here we are multiplying the first row. Here is the first, A11, A12, A1n. We are multiplying that by constant k and adding that, let's say, to A21. Here, k, A1, 1, 2, and add it to A22. And do the same thing here, k, A1n, and here add it to A2n. 2, 1, 2, 2, 2n, yes. So if you think about the determinant of B, and you focus on this row here, what are you going to get here? You are going to get determinant of B is going to be, I'm going to use this row to write the determinant here. So that is going to be k A11, I'm going to write that in details, A21 multiplied by C21. Now, C21 here is going to be the same as C21 here, correct? Because the first row is the same and the other rows are the same. The only difference is this. And this, when you find C21, you are going to cover it, correct? So that will not change. Plus K A12 plus A22 multiplied by C22. Again, C22 is the same as you have it here. And you keep going here. Plus K A1n plus A2n and here C2n. All right, so that is going to be the determinant of B. Now, look, what happens when you unfold this? When you unfold this, you are going to get this multiplied by this and this multiplied by this. Okay? Now, this multiplied by this here, and this here, and this here, actually this with this together, that is the same as the determinant of A. Now, we are left with the effect of this here. This when you multiply it by this, and this. Now, what is that? Look at it. The k is not a problem. The k, you take it out. So what is left here? What is left is this. So the conclusion here, determinant of B is going to be determinant of A plus k into something, which is A11 C21 plus A12 C22 plus A1n C2n. Now look at this. What is this? Remember, C21, C22, C2n, they are the same as what you have here. So now you have A11, A12. What is this? This is coming from the first row. So this actually, it is the determinant of a matrix in which you have this row and this row same. So basically, to understand what is this, you need to think about what is the determinant of a matrix that has a repeated row. Right? So you have a matrix that has a repeated row. What is the determinant of that matrix? To answer my question here about this, you need to address this question. You have a matrix in which two rows are the same. They are repeated. What is the determinant of that matrix? Well, the determinant of that matrix, you can get it from this. This, it says if you interchange two rows, you are going to get a negative sign. But the two rows, they are the same. So when you interchange, you will get the same matrix, actually. Correct? So here, determinant of B is going to be the same as determinant of A. So you have determinant of A equals negative determinant of A. Move this to the side, what do you get? You get 2 determinant A equals 0. So what's determinant A? Determinant A is going to be 0. So here, maybe I should write that as a fact here. Important remark, this is 1, this is 2. If you have a repeated matrix, a repeated row, n, an n by n matrix, matrix A, then determinant of A, okay, I'm going to write it small d, determinant of A is 0. You can verify it from here, okay? Now, use this fact here, you are going to find this 0. Okay, so now what is the effect of multiplying a row by a constant k and add it to another row? Well, it is going to be, this will be 0, so you get determinant A equals determinant B. Okay, so here you get same determinant. Let me write it here. Determinant of A equals determinant of B. So now here, in conclusion, let us summarize this. You can do 3 elementary row operations. What is the effect of each one of them on the determinant? If you multiply a row by a constant k, then the determinant of the new matrix is going to be k multiplied by the determinant of the old matrix. If you interchange 2 rows, then the effect will be a negative sign in the new determinant. And if you multiply a row by a constant and add it to another row, what is the effect on the determinant? There is no effect. Okay? So now, after understanding those 3, and the verification is very easy, okay? After you understand those, you can do elementary row operations and trace your steps and see the effect in each step and get the determinant of your matrix. Okay? So let's do an example and we clarify those in a concrete example. So I'm going to take a matrix. I'm not going to do the elementary row operations step by step, so I'll just write them down here, or I can use the computer to show you that. So let me do it. All right. So here you have a matrix in front of you, and I did the computations here on the computer. You have many places online or many softwares in which you can do that. So let's take this matrix here and trace the elementary row operations and see what is the effect. So we started here with the matrix A. You have it. So the matrix is 1, 2, negative 1, 1, 2, negative 1, 0. Then 4, 2, 4, 2, negative 1, 3. And then 3, negative 2, 0, 3, negative 2, 0, 1. And 4, negative 2, 4, negative 2, 5, 3. And now, doing elementary row operations. Add 4 times the first row to the second row. What is the effect of that? You are multiplying a row by negative 4 and you are adding that to another row. What's the effect of that? No effect. So here, let's say the first step. 1, no effect. Okay. Add negative 3 times the first row to the third row. Has no effect. Add negative 4 times the first row to the fourth row. You are multiplying a row by number, adding to another row. Has no effect, based on the rules that we found. Okay, multiply the second row by negative 1 over 6. Multiply the second row by negative 1 over 6. Okay, so here we are not adding to another row. We're just multiplying one row by negative 1 over 6. So here is A. Now, so step 2, no effect. Step 3, no effect. Step 4, multiply by negative 1 over 6. What does that mean? It means determinant of A, determinant of B is going to be negative 1 over 6, determinant of A. The new matrix you got here is going to be negative 1 over 6 multiplied, or the determinant of the matrix B is going to be negative 1 over 6 times the determinant of A. So this is the effect of this step. Add 8 times the second row to the third row. Has no effect. So step number 5 has no effect. No effect. Okay, let's move on and see what is next here. Add 10 times the second row to the fourth row. Has no effect. Multiply the third row by negative 1. What is the effect? So here, then, negative 1 over 6, determinant of A. From this step, the effect is you multiply by another negative 1 here. From here. Now, add negative 4 times the third row to the fourth row. Has no effect. Multiply the fourth row by negative 1 over 14. So what is the effect? You multiply by negative 1 over 14. So here we are. Add negative 3 times the fourth row to the third row. Has no effect. Add 1/2 times the fourth row to the second row. Has no effect. Add 1/2 times the third row to the second row. Has no effect. Well, as you see here, maybe I went too far here. I don't need to keep going, because you can see here echelon form. You can take any one of those as your echelon form. So I can stop here. Look. Here I have an echelon form, or I can stop there. Okay, I can stop here now. This is a triangular matrix. What is the determinant of this? You multiply the elements along the diagonal, so it is 1. So this is going to be triangular matrix. And I'm going to call that determinant of D, or T, or whatever you want to call it. And that is going to be 1. So, determinant of A, then we multiply that by negative 1 over 6, then we'll multiply that by negative 1, then we multiply that by negative 1 over 14. That ends up with a matrix that has determinant 1. So, in this case, hence, determinant of A is what? Negative, negative, negative. So that is going to be 6 times 14, and you have negative. Negative 84. That is 6 times 14 is 84, and you have negative sign. So the determinant of your matrix is negative 84. Okay? Just you trace your elementary operations, and you see the effect of each one on the determinant. All right. That's about elementary operations and the effect on the determinant. Here you have an example, so now you can do other examples and other exercises. Let A be an n by n matrix, and E be an n by n elementary matrix. Matrix. Okay, so we have a square matrix in general, and we have an elementary matrix of the same size as your matrix. Okay. Now, what can you say about the determinant of E? Determinant of E. E. Remember, E is coming from the identity using a single elementary row operation. Now, we know what is the effect of each elementary row operation. What is the effect? It is going to be one of the three things. Either you multiply by k, or you multiply by -1, or no effect. Correct? So, in this case, it could be that you are getting E from the identity by multiplying a row by k. And in that case, the determinant will be just k multiplied by the determinant of the identity, which is 1. So this could be k. Or it could be -1. Or if it is no effect, what does it mean? It means it's the same as the determinant of the identity. It could be 1. Okay? So this if you multiply a row by constant k, this if you multiply a row by, if you interchange two rows, and this if you multiply a row by a number and add it to another row. Okay? So the determinant of any elementary matrix is going to be either k or -1 or 1. By the way, this is we can put it as a multiple choice question. Suppose that E is an elementary matrix of size n by n. Determinant of E is, we can give you options, okay? Remember, it has to be one of those, either k or -1 or 1, okay? And k here, it is coming from the elementary row operation in which you multiply a row by k, and that's it, okay? All right. So that's very easy to observe. Here's my question. So that's, you can say fact number 1. Here, fact number 2, determinant of EA. What is that? Determinant EA. Remember what we said about multiplying by an elementary row operation. We said this is the same as doing an elementary row operation on your matrix, correct? So if you have a matrix and you do an elementary row operation on it, that will be the same as multiplying by an elementary matrix, correct? And again, using the previous discussion, we can say here that is going to be the same as the determinant of A, or the determinant of A multiplied by -1, or the determinant of A multiplied by K. And in this case, that is the same as saying determinant of E multiplied by determinant of A. Correct? That's very simple fact. However, this is very important now. It will help us to prove a result that is more general, more sophisticated. Okay? So let me repeat myself here. A is an n by n matrix. E is an elementary matrix of the same size. So what I here did, I clarified that determinant EA is the same as determinant E, determinant A. Why is that? Because that is going to be the same as doing an elementary row operation on your matrix, and that is going to have the effect that we discussed before, and that is going to be the same as what I'm writing here. All right? Okay, so now, big theorem or nice theorem. Let A and B be two n by n matrices. Determinant of AB is the same as determinant of A, determinant of B. That's a very nice fact. The determinant of the product is the product of the determinant. The determinant of the product is the product of the determinants. Why is that? Why is that? All you need is just to think about what we did before when we did elementary row operations. Think about taking A and you do elementary row operations. Okay? So when you trace the elementary row operations, the effect of each one is going to be like multiplying by an elementary matrix, correct? So here you have the matrix B. So write A as E1, E2, E3, E, let's say K. And at the end, you are going to get a triangular matrix, correct? The triangular matrix, you know the determinant of that. Well, the triangular matrix could be actually the identity matrix if you have ones along the diagonal. And in that case, this will be here the identity actually. Okay? That if your matrix A is invertible. If your matrix A is not invertible, you are going to get a row of zeros. And in that case, the determinant is 0. Correct? So basically here you can relate that with the invertibility of the matrix and see what is the final shape of the echelon form or reduced echelon form that you get here. Okay? Now, whatever it is, well, maybe I should split it into two cases. The case in which you have a row of zeros, so in that case, the determinant here will be 0, the determinant of the final form you get here, okay? But that means your matrix A is non-invertible. And remember, last time we talked about if you have two matrices and both of them are invertible, the product is invertible, okay? If one of them is non-invertible, the product is non-invertible. So you can use that to conclude that if the determinant of the final form here is 0, then actually the determinant of this is 0. Okay, so the case in which A and B or A is non-invertible will give you a zero determinant in the final echelon form here, and that means the case we already handled, okay? Because it means the product is non-invertible and we're done with that. However, if the final form here is the identity, then in that case, you can write A as a product of those, okay? Those guys here. If you want to combine both cases in one, you can do that. Just here you have to think about either you get the identity or you get a diagonal matrix with zeros along the, or some zeros along the diagonal. But yeah, we can combine them, both cases in one case. However, either way, A can be written as a product of elementary matrices times here, just for the sake of being accurate here, let me write here times T. Okay, where here T either identity or triangular. Triangular with a zero along the diagonal, with the zero row. All right, so now all you need is just to write here AB equals EK minus 1, E3, E2, E1. And that's when we have the identity multiplied by B. And in this case, determinant of AB. You apply this, you get determinant of EK, determinant of EK minus 1, determinant of E1, determinant of B. But what is this? This is determinant of A multiplied by determinant of B. Okay, so that's very easy to prove using this fact. Okay, and together with the fact that when A is non-invertible, you get here the product is non-invertible and the determinant is 0. Okay, so you can exclude that, and in that case, this will be a good verification using this fact. Okay, so from now on, the determinant of the product is the product of the determinant. Okay, what about this? Determinant A plus B, is that same as determinant of A plus determinant of B? Is the determinant of the sum going to be the sum of the determinant? No. Give an example. So don't go too far, just think about an easy example. 2 by 2 matrices, two 2 by 2 matrices, and see what is the determinant of the sum, and see what's the determinant of each one of them, and see that the determinant of A plus B is not necessarily the same as determinant A plus determinant of B. Okay, so I leave it for you here to take an example and counter example and see this is not true in general. Okay, all right, so I'll stop here with this very interesting fact: determinant of AB equals determinant of A, determinant of B. Next time I'll discuss more properties that are nice properties about determinants, and then we start to use the determinant in a few other things that will help us to handle linear systems. Okay, we need to use the determinant now and relate it with linear systems and see how is that going to help us. Remember, everything we do in this course is related to linear systems. We go back and we relate it to linear systems. All right, that's it for today. Have a good day, guys.